Good morning all. Myself Dr.Jyoti working as a head department of mathematics of this university. I heartily welcome you all in this mathematics popular lecture week organized by the Department of Mathematics to celebrate the National Mathematics Day. This we were organizing every year to celebrate the birth anniversary of a great Indian mathematician, Professor Srinivas Ramanujan. Along with the Mathematics Popular Lecture Week, we were organizing a mega competition consisting of poster presentation, seminar, and quiz competition. I heartily welcome the guest speaker of this today's eighth lecture of this popular mathematics week, Dr. Subhash Kendre sir, professor from the Department of Mathematics, Savitribai Phule, Pune University, Pune. I heartily welcome all the students, faculties, and participants for this program. And I request Mr. Vinay Kandi sir to give the introduction of the guest speaker, Dr. Kendre sir.
Thank you, ma'am. So, good afternoon to all students and respected sir and madam. So, Punyashlok Ahilya Devi Holkar, Solapur University, Solapur, School of Computational Sciences, Department of Mathematics, organizes the popular Mathematics Lecture Week on the occasion of National Mathematics Day 2021. So, today our speaker, Dr. Subhash Kendre sir, professor at Department of Mathematics, Savitribai Phule, Pune University, Pune. So, sir completed their PhD in some problems in the theory of nonlinear system of integral equation. Sir have a 17 years of experience of teaching and research at Department of Mathematics, Savitribai Phule, Pune University, Pune, and 2 years of UGC project fellow at Department of Mathematics, Dr. Babasaheb Ambedkar, Marathwada University, Aurangabad. The thrust areas of research of Sir is differential equation, integral equation, and integral inequalities. Under the guidance of Sir, 4 PhD students and 3 MPhil students are awarded, and 3 PhD students working now. So up to now, Sir completed 3 research projects under the various institutes, 35 research publication, 10 PhD and 3 MPhil thesis evaluation, and 11 paper presentation, 6 international, 4 national, and 1 university level. Sir also have a life membership in Indian Mathematical Society and Indian Science Congress Association. And Sir also got this special awards, Professor Chintaman Vishnu Limay Prize and Giridhar Rao Deshmukh Prize, first in MSc Mathematics in 2001. So this is the short introduction of today's speaker. So thank you. Thank you, ma'am. Over to you.
Thank you, sir. Now I request Dr. Kendre sir to please start the session.
So thank you, ma'am and sir, for the kind words and giving the introduction. So once again, I thank you for giving me this opportunity to speak in front of these students from the Solapur University. So today I'll speak about just introduction to the dynamical systems through so we'll starting with the differential equation part. So I consider that all of you know the differential equation, at least from the coding theory, basically differential equation, classification of the differential equation, then a linear, basically classification is linear type of and non-linear type differential equations, then first order differential equations, second order, nth order differential equations with constant coefficient and variable coefficient. And certain there are various methods to solve their solutions. Someone's sound is coming. So I consider this basic knowledge from the differential equation, and I'll start with the analytical and other approach type of the differential equation basically. So first concept is directional field. Directional field. So you might be familiar with, some people may be familiar with, but I'll repeat it. Directional field. So actually due to this open board and pen and pencil, handwriting is a little bit cursive, so please bear with me. So some spelling and all this, because it is just a technology, so we are using. So direction field, first what do I do? So you are familiar with y dash equal to f of x. I'm sure that everyone is familiar with this equation. Y of x0 or t0 equal to y0. Okay, so this is the initial value problem you discussed at your in the MSc course or at the BSc level also, right? So I'll not go in the detail related to this is ellipses and all these things. I just consider this is a differential equation that you studied the Picard's theorem, existence, local existence, and all these things. I'll not go in the detail. At least for the first order, I give we'll discuss a little bit about the first order, and then we'll go to the linear system of equations. Okay, so bifurcation and all these things. So here y dash means this is y. We use y dash equal to dy by dx, right? So geometrically, so what about the interpretation of the derivative? It is the slope of the tangent at that point, right? Slope of the tangent at that point, right? So this is the interpretation for the derivative, right? So here in this equation, so we have dy by dx equal to f of xy. So this all the y is a function, x is this f defined will not go dt. So this is dy by dx. Now this is the slope of the tangent at that point. So but what is this? This is equal to f of xy. That means our derivative dy by dx is equal to f of xy, right? So this is dy by dx equal to f of xy. So it means, so this is the slope of the tangent at a point xy, right? So at what point? So f of xy. Okay, you choose x and y points, and you can calculate any point. See, this is x and this is y, and at these points you find the value of x, right? So f at this particular point. So that way, so the slope is there, right? Clear? Or for each x and y, and means for this means particularly we can find these values of f of x. If you choose x and y, and you find the value here, or in particularly x is there, and if you have solution y of x, so means at particular x you have these values, right? So means if you collect these things, f of xy, right? So these values and this value of this particular function at xy will give the slope of the tangent at that point. So geometrically, the interpretation of the solution means, now in other words, the solution of this differential equation, in particular, a solution of this equation is a function phi, I'll say, whose graph is a curve, right? So it's f of x equal to some curve, right? It's a curve. The solution function phi whose graph is a curve whose tangent at the point x comma phi of x has the slope phi dash of x, because we know that phi dash of x, which is same as the given slope at f of xy, f of given slope at f of x comma phi of x, right? So this interpretation is there. So you are not actually not mentioned anywhere. So geometrically, we give a set of directions. See, in this case, so geometrically, we give a set of directions of the differential equation, right? So this f of xy gives the different points, right? Directions of the differential equation to the problem of finding a curve having these directions. Means in particularly, suppose if you instead of going to the detailed theory, will discuss the one simple example. Here, y dash equal to minus of xy, right? So this is 0, this is x, and this is y, right? So at what? So you f of xy equal to, this is minus xy. Now, so if I do one thing, so this is 1, right? So 2 and 3. If you know if you understand this direction field, so you'll understand the bifurcation also. This minus 1, minus 2, and 3. So here also 1, 2, 3. We can take only positive part or negative part also, it doesn't matter. So for this particular problem, without solving this equation, right? So without solving this equation, we can geometrically find the solution basically here. So see, at 1, 1, for x equal to 1, y equal to 1, what about the value of f of xy? So its value is minus 1, right? So minus 1 is the slope at this point. So where is this point? So this is 1, right? 1, 2, and 3. So this is the slope. So minus 1 is a slope, means it is going down, right? Similarly, if I choose 1 minus 1 point, x equal to minus 1, and y equal to, see, I'm not going to solve these examples. Just I am looking at their using the nature, looking at the differential equation, we can plot this thing. So this is minus 1 and this is 1. This is a point, and I'm drawing the vectors there. That will give you the direction field, right? So here this point is there. So this is minus 1 and 1. But what about the value here? It is minus x, it is 1. So the direction is, if you draw the direction, you know that vector algebra, you know that if the 1 is the slope, then how do, when here now what we get? Well, we get the slope is 1, and you find here the like this, and here it is down. Now similarly for 2 and minus 2 also you get this way, right? Here also you will get above way, right? Like that. So here also minus 2 and 1. See, minus 2 and 1, minus 3 and 1, like this. So you'll get like, and so on. Here you go like this. So accordingly you will get the directions. I'm just calculating these values only because of we know that. So 3 like this, above here. So this is one example. And if I solve this example, you'll see how it is without calculation. I calculated the solution. I take a simple example here. This is just see. So what y dash equal to f of xy. F of xy is minus xy, and you find the value of f of xy at different points. X equal to 1, y equal to 1, x equal to minus 1, and all these points. So particularly you choose y greater than 0. So for negative also you can see it. There is no problem. But now if you see like this here also, so you can see this way. Right, this way. You just see what my intention is. If I means this is a direction, actually this is a vector here. What is the vector? I'm just drawing the vector at that particular point. You choose this point and this point. So this is here, this point, and calculate the value. Depending upon the value, that value gives the slope, right? Slope at that point. So we know if your slope is given, you can draw the line. So you just draw the line arrow. You may draw the arrows also. No, there's no problem for that also, right? So in this case, you'll get like this. Now here, so this is a vectors. Actually, this is a vector field. Now how it see how it is useful for the solution set is, you'll see it. Now other approach now. So I'll show you. So anyone can tell me the solution of this equation? Yes. So y dash equal to xy. So this is dy by y equal to minus x into dx, right? So dy by dx into x. So this is log of y equal to minus x square by 2 plus constant c. So this is y equal to e raised to minus x square by 2 into e raised to c. So this is k into e raised to minus x square by 2. Right? So this is the solution. Yeah. So we have y of x equal to k into e raised to minus x square by 2. So we can find k whenever some initial condition is given. So in particularly, if you y of 0 equal to 2 is given, so what we have, y of 0 equal to 2 means k equal to 2. So therefore, the general solution of y of x equal to, for the initial value, this is 2 into e raised to minus x square by 2, right? So now you draw the graph of this solution. Now this known solution, see this, sorry. So the graph of this function y of x equal to 2 into e raised to minus x square. So in this field we'll draw. So at 0 we'll get 2, right? Here at 1 we'll get, see here. So if you draw the graph of this, it will be like this simply. So this passes through these directions, see, simply. So as per the flow of this field, see. So this is y equal to 2. So you may take y equal to 3. You'll see this. Different things it will slow. This will be like this. Okay, so like this. So this is one thing. So just I need this direction field. It is nothing to do with the dynamical systems, but you know the direction field because we have to draw the phase portraits. These are the phase lines. If you change y of 0 equal to 2, y of 0 equal to 3, y of 0 equal to 4, you may draw like this. So this is, see, it is just, if you now, actually these lines are joining, this passes through these vectors, these vector fields. So this way. Right? So they are tangent at that point. So that way we often see the e raised to minus x square. So general graph of e raised to minus x square is x square by 2 is there. It is a normal distribution if you see, right? So this is the graph of the e raised to minus x square. So it is minus x square by 2. It is similar to that way. Okay, into 2 into. This way it will go like this. So this you see. Without calculation, if you see, this is a simple idea. Without calculation, so this we have drawn these pictures looking at the example only. So now the definition I give you. So direction field, the set of directions directions. This set, this is f of xy, right? So this is a set you find for all values is called directional field. For y prime equal to f of xy. Okay, so this is the important point. This see, this is a directional field. So how this actually just solving the method, solving example, you have to look at the nature of the solution also, right? So this is the thing. So other examples you may discuss, no problem, like other examples also. Okay, so this is one point we have to, you understand what I'm saying? A direction field, it is a collection, the set of directions f of xy. So which are these? So these points. So this that actually just what I said, f of xy is equal to minus xy, right? And you find the values of f of xy for all x and y, right? You will get, and that value gives the slope of the tangent at that point. And using this slope, you draw the just a line, straight line, slope of the tangent line. You draw the line, right? Then you will find that. So then you'll find the solution, means the solution curves passes through these tangent points, right? So these directions. Okay. So this way, it is a first point. Means apart from the our classical thing, generally we look at the y dash plus ay equal to 0. So then r plus r minus a equal to 0, e raised to minus x with calculate the solution. Even so, this is a case where we able to solve the equation. Suppose, for example, y dash equal to sine y. How we'll draw now in the nonlinear case? This example we have discussed, right? So suppose y dash equal to sine y. So this is a nonlinear equation, but we can calculate the values of sine y for all x1, right? And that case we can draw whatever the directions are there, and we can predict the solution. Which curves pass curves, we can draw the curves through these directions, right? So this example I have discussed simply for the linear equation because we can able to it. So, but so why we study? You are saying why we are studying these complicated things? No. So these are really useful things for the different type of problems which are non-linear type. See, y dash equal to sine y are different. Means we are not able to calculate the directly the solution of these differential equations, right? So this thing is useful. So I suppose you understand what is the direction field for the differential equation. This is nothing new. We have considered the simple first order differential equation, right? Instead of going through the usual formulas and calculation of the solution, I used the geometry here only. Geometry, that is like slope and tangent, all these things. So how we use? I calculated the value of f of xy at these x and y points, various points. I have drawn the tangent slopes, actually the lines with the given slopes, right? Short point like at that particular point. So you may like this arrow also, not if you are if you want like this. So this way you can study. Okay, so this is the one thing. So another approach I want to discuss now, the bifurcation I want to discuss now, another thing. So another simple example I want to this analytical way. Another simple example I'll take here, y dash equal to ay. So, but what is a here? A is not a constant. A is a parameter. Okay. Example. See, generally, whatever, instead of going to the just the theory and proofs. So, if you look at the examples, the things will be more clear, right? Y dash equal to ay, and you may consider this is the initial value problem. No problem. Y of y is x0 equal to y0. So this is. But what is a? A is a parameter. So we can, so this is a linear equation, existence uniqueness is there, no problem for that existence and uniqueness thing, right? But here, in this case, what about the, without looking at the initial condition or with initial condition also, y of t equal to, I'll directly write some y0 into e raised to at is the solution. So if I'm not wrong, like that, right? But here A is a parameter. So this approach is different. See, whatever I am discussing is different from what you studied at your MSc level, means from the Codington or other Siemens book like that. Here is, you studied this problem. See, y equal to 5y, right? Y dash equal to 5y. That 5 is a constant, but no. Here A is a parameter. A belongs to R, like this. A is a parameter. For different values of A, what about the nature of the solution? So that here, okay, so this simple example I'm taking. So now the solution behavior of the solution is one, first point. If a is greater than 0, Okay, so you may choose, you are free to choose. Then limit that x tends to infinity, because this is x and y, so this is like a y dash equal to f of xy of this y of t, sorry, y of x, sorry, here. Okay, so if you take t, then this is t0, so no problem for that, t0. So then here you have to take t0, t tends to infinity, y of t equal to limit t tends to infinity, y0 e raised to at, right? As a is greater than 0, so this is equal to infinity if y0 is greater than 0, and equal to minus infinity if y0 is less than 0. So this is analysis, right? So behavior of the solution, see, depending upon a. Now second, if a equal to 0, then limit again. Limit. Okay, so a equal to 0. So if I choose a equal to 0, so then obviously this y dash equal to 0, right? So this gives you y of x or y of t is constant, right? So this is a constant. So that means y0 into e raised to at is constant. Third one, so I'm going to stable, unstable type of solutions, like so. This is needed here. If a is less than 0, then limit x, sorry, t tends to infinity, y0 into e raised to at equal to 0, right? So this is actually, this a is less than 0, this is a stable, right? Here a tends to infinity, this is unstable, and here constant, it has something different. So that part is not studied in the classical case, that part will study in the system of equations basically. So this is a center thing will come to the picture. See, so this way, this is the classic analysis of the solution. See, as a greater than 0, so the solution tends to infinity, either plus or minus infinity. If a is less than 0, in both cases solution tends to 0, which is a stable solution. Okay, and a equal to 0, the solution is constant for this equation. Now what about the phase planes for this example? So we discussed a direction field now, so we can draw the phase planes. Means actually, what is a phase plane? I'll show you first thing. So this is a phase plane, phase portrait or phase plane of the solution, initial value problem. These lines are called the phase planes. Solutions means basically these are the phase planes we'll draw for different values of initial values there, right? So see, without line, this is a direction field, and if you draw the solutions curve passing through this, so this represents the phase plane of the differential equation. Okay, so this thing, now we'll draw these phase planes also. So phase plane, or direction field first and then phase plane. Phase plane or phase portraits, or just basically the direction field. So you look at these names used there many places. So we'll go for different two things. First, we'll calculate for a greater than 0. So we'll see now. So looking at the definition, we'll not understand the solution is stable, unstable, or that particular point, right? So I'll draw the pictures here now first. Geometry, actually it is the now x and y. Okay, so this a greater than 0. So a greater than 0, what happens? A greater than 0, x tends to, depending upon a greater than 0 and y is a greater than 0, and we'll fix y0 now. So that y0 will fix something, so we'll not bother about it. So we'll take up the positive thing. So because it's anyhow, it is a constant, so it will not change anything else. If it's negative, it's just opposite thing happens, right? So a0, y0 will fix it. Now in that case, the solution again, so my first thing is y dash equal to ay, right? So a greater than 0. So looking at y, for values of y, right? Y equal to 1, slope is 1, y is minus c. So here slope, even if you go here, what will happen? See, y xy for any value, sorry, for any value of above this thing, right? See, y is here is 0, right? 1, 2, 3. So above this, so this is like simply the slope, it will like this only. Direction fields are like this. Even here also. Here you calculate also. This is the, and if you go for the y is negative, means here this value, and this value. So it is like this only, because you can see, we know that how to draw the, so if slope is given, how to draw the line for this. So this is the direction field for this equation if a is greater than 0, and then the solution passing through these lines for the different values is, sorry, actually it is moving, my pen is moving. So this line, actually the solution passes through these things, so they are like this. So these any two solutions never crosses each other, intersect anywhere. See, like this. And for the below it is like this. Imagine they are passing through these points. Okay, on the board it is very easy, because this is moving pen, and board is actually, this is difficult still, because of the long, still I'm able to do draw the good pictures because of the practice also from last 1 year doing these things. Okay, right, now see y is positive, you'll get the positive slope type, negative like this simply. Okay, so now if you see, this is a x now, so if I draw here this straight line 1, and I have this point particularly, so this is a particular point. What happens here, solutions going away from this particular point, right? So I can draw, this is analysis basically. So when we discuss this, now the next point is we have to discuss the source, sink, and equilibrium point. See, so for a greater than 0, solutions are going away, right, here towards the infinity, and if it is for the, if y in the negative thing, y is for this, it is going to the minus infinity, right? So like this. So this is going away, solutions are going even like this also. If you draw here also, it will going away from this here. Exactly, you will get the symmetric picture. So they are moving away. So this is the phase lines, or if you, actually this is possible without looking at the calculation of the solution, we can draw these things, right? If you use any softwares are also there, so one can draw these pictures basically. Okay, so this is one thing. So another, we'll go for the a is less than 0. Still, now again, so this is x, this is y, right? And okay, so this is like this. So what will happen, a is less than 0, so that means y dash equal to ay. A is less than 0 means a is negative, right? So in this case, whatever you choose y, so it's 1, 2, and 3, so that will be the minus, right? So that means if you 1, 1, right, at this particular point you will get like this. So this way down, always you will get like this here also, because there is no x involved, so there is no effect of x on the, like this. If I draw the direction field here, now a is negative, so sorry, a is negative, and if you choose y is negative, so negative becomes plus, so the slope is like this now, upward direction anywhere here now, because y is x is independent, right? This is the independent thing in this particular example. So other examples it may work like this. So if you draw the phase lines, so from this way you'll get something, it will not cross basically. Okay, so because of this plane it's coming down, so like this, so then again passing through like this, and so on. These are the phase lines. If you see, to draw the picture 1, 2, anything, no, I'm not just, this is from the values of y, actually this is from the values of y. See, these are the phase lines basically. So this actually, if you see, this is our image. Now see here, what happens if I draw now here, again this at the same point particularly, sorry. So at this particular point, so if again we'll draw here, so at this particular point, what happens? Solutions are coming towards the origin, right? If you see the solution coming as, see, definitely one thing we have to clear, at x tends to infinity, we have to look, x tends to infinity. So these solutions are coming towards here. This way happens. So this is coming. So this, if you are coming towards, it is a sink. This point is called a sink. We'll go to this previous thing. So this point going away from, it is a source. It is actually, the solutions are going away from this origin, right? So this is source. This point is called source. Okay, sink and source. So this is source, right? So see, sink means sink. Actually, if you see, imagine the sink. So it takes the everything at a point, a particular point. It collects this thing, and source, it is going away. Sun is a source, right? Like this. So this is the thing, and this is sink is a stable, source is unstable. Okay. So this way we have discussed these things. So then using this, actually after this example, we'll discuss now the points basically. There are systems basically, again, if you consider y dash equal to f of xy, right? So this is a non-autonomous, and if y dash equal to simply f of y, then it is autonomous. Autonomous system. This is a non-autonomous system, and this is a non-autonomous system, right? Then scalar autonomous system also we can define y dash equal to f of or fc of y. This is a scalar autonomous. Autonomous equation, right? So this different way, actually they're looking at these equations in a different way. So just see, in the in mathematics, actually the studying of mathematics in the two different ways are there. One is in applied or representation way, and another is just stating the theorem and proving and solving the examples using formula. There are two different ways are there for the studying the mathematics basically. So if you visualize the things, so you'll understand very rigorously here now. So this is autonomous, this is non-autonomous, and scalar is there. So this first example, why we did y dash equal to ay, it is a scale. This is a scalar autonomous system we discussed, right? And for this system, we can find what is the equilibrium point. So then we'll give you the definitions of these things. Yeah. So and I have not introduced anything new still. So we are just discussing whatever you studied in the first elementary course of the differential equation in the first few lectures only. Not in the even the last chapters also. Just the first few lectures you discuss these differential equation part. Scalar autonomous system that we have discussed. Now, what is the equilibrium point? If as this particular problem, y dash equal to ay, right? So that y equal to 0, right? So this y equal to 0. So what will happen? Y dash equal to 0, right? So that means y equal to a constant, right? So see, you consider this concept and look at this definition. I always try to give example and then give the definition basically. So this definition. So whatever we discuss the problems, so the definitions are depending upon that. This is a constant solution, right? Y dash equal to 0 means y equal to 0 is the solution of this differential equation. A constant solution or a steady solution of above equation, right? So above this of this y dash equal to, you may consider f of y or f of cy also, it doesn't matter. F of cy is called equilibrium point of this equation. Okay, so this is one, a constant solution. So this is y. So for this example, y equal to 0 is a equilibrium point. So this y dash equal to ay. So this y equal to 0. So we'll not, this a is a parameter, will not restrict because we allow a to vary. So y equal to 0 is a equilibrium point. Is an equilibrium point. So another example, y dash equal to y into y minus 1. Here y equal to 0 and y equal to 1 are equilibrium points. Okay, so and the same way you define different things, so that way you can define it, right? See, if we put y equal to 1, so this y dash is 0. So in alternate way, actually in the other way around, so instead of that, y0 is an equilibrium point of this one. Okay, so this equation of y dash equal to f of y or f of cy, if and only if f of y is 0 or f of cy 0 is equal to 0. So this is one of the same thing what we are doing. See, f of c, fc of y equal to 0. So in general also, if you have this equation, see y dash for autonomous y dash equal to f of y, so, right? So then f of y equal to 0. You find all solutions of this equation, so that will give the equilibrium points. Okay. Clear? So we discussed this equilibrium point. Now, so this is equilibrium point. And then this example, if I go to the previous, again, I'll go to this example, what we discussed. So this is, see, in this example, so this 0 is equilibrium point, right? So this y dash equal to ay, right? So y equal to 0, equilibrium point. Right? So then now further classification of this equilibrium point. See, so this solution is stable. So then, or this way, the solution going, this equilibrium point is called, see, this is unstable, actually going away from this origin, right? The solutions are going away from the origin. Generally, you draw these pictures. So this is called a source. Okay, so this particular point in this case means particularly a greater than 0, y equal to 0 is the equilibrium point of the differential equation, which is source. Another, see, where we discuss this. Oh yeah, this one. Okay. So now this point you see. So this again the same example. A is less than 0 and y equal to 0. So this is a sink. Right. So this is a stable, and this previous one is a unstable. So this part is basically this is required a little bit. So or another thing about this problem, the bifurcation. We can say the bifurcation is there. The slight change in this parameter. Where is the where is the okay, so we'll discuss that part later on. So little bit before we go to this, so you will understand what is the sink, what is the source, and what is the equilibrium point for this differential equation. Now our main task is to linear system of equations now. So this part we need here because the direction field, then equilibrium point, and the stable and unstable things. So now the linear system. So what is our approaches? Linear system of equations. So you know the linear system of differential equations basically here. So I'm talking about not the general. Otherwise, you'll say that x plus y plus z equal to 0. No. Linear system of equations. So just like a y dash equal to ay. What is a? Is a scalar, right? So you consider this is a scalar or constant. So how the matrix actually there's a linear system of equations are there, right? Particularly if I choose x equal to x1, x2, and xn, a equal to, so a equal to some a1 to a1n, right? And I'll choose an1 to an. So this matrix is there, right? So then x is a, we know that x is a, this is column vector, right? So if I calculate this x dot equal to x dot, right? It's a derivative, so we know that it's a derivative and integration as coordinate wise, like that. So I can write this equation as x dot equal to ax. Okay, you see this is a matrix. So that is, I'll write x1. If I simplify this one, so x1 dot equal to a1 1 x1 plus a1 2 x2 plus so on plus a1 n xn, or x2 dot equal to a21 x1 plus a22 x2 plus so on plus a a1 n, here a2 n xn, and so on. So this is linear, right? Or in other way, I'll write general also, xn dot now equal to an1 x1 plus so on plus an n xn. So this is the system of linear equations, differential equations, right? In other way, if I choose x is in Rn, so in simpler manner, I want to, if I choose x is in Rn, right? A is the n by n matrix, or instead of that, so I'll just go for the functions also. If I have equations like this, x1 dot equal to f1 of x1 x2 xn, or t also we may write. So this is autonomous and non-autonomous thing. We'll write so t comma x1 x2 xn, x2 dot equal to f2 of t x1 x2 xn. These are system of equations, and then xn dot equal to fn of t comma x1 x2 xn, right? If I denote here, so we can write, so this also we can write, if I denote x equal to x1 x2 xn, it's transpose, right? And capital F equal to f1 f2 fn, it's transpose, then we can write this equation as x dot equal to f of tx. So this is a system of equations, but we don't know about this linearity and all this. Now it is linear, right? If it is linear in x and y, right? The simple case is x dot equal to ax. So this is a matrix equation, x dot equal to ax. So this is the linear equations are there. So this is non-autonomous because t is there, and if I write x dot equal to only simply f of x, so this is autonomous. Okay, but we'll not go in the detail. I'll discuss this non-linear part also, how it depends upon the this particular thing. So we'll see this now. Now, simple example. I'll not go. See, here is no time to discuss state the theorem and give the proofs in detail. No. So actually generally what I do, I give the examples and I'll discuss the state the theorems directly there. So in proofs are the actually the proof. You can go, you'll collect from the any book or from the literature also basically, right? So in a simple case, if I take this example, 2 by 2 or 3 by 3 example, okay. So see, our notation is x dot equal to, so this is the thing, dx1 by dt, and so on, dxn by dt, right? So this is the dot, and we know that A has a matrix, n by n matrix, this thing. And our problem is simply we concentrate on this problem only, Ax. Okay. Here, if I compare this example with y dash equal to ay. So what is A? A is a matrix. This is a constant matrix. What is A? A is a scalar. Constant. See, this is a constant basically, right? Now, its a solution is y of x equal to some constant, right? Or y0 into, right? So it's just y0 into, if you have y at x0 equal to y0, so then y0 into e raised to ax, right? So this is the solution. Or you write in terms of the t then, so instead of t, because we have to write here also. So this is t0, this is y0 into a raised to t. So what do you expect from this particular thing? Right? So can you imagine the similar result? Can we expect the solution of such a differential equation, right? So they arise naturally in many cases. So this is, see, there is another actually the way of discussing and modeling the any phenomena. So there are, that is from the physics, engineering, and various fields are there. So we'll not. So this is not our work for the mathematics. So our work is to, whatever the problems are there, just look at their examples, and we are not dealing with the pure mathematics people. Not do these things. So what this problem we have, so how to find the solution, analyze the solution, characterize the solution, and study the behavior and various properties of the solutions. That is our main task, right? So this is the thing you compare. Now you just imagine in mind, one is example is x dot equal to x and another is y dash equal to ay. So this is a, here y is from r to r and here x is from rn to rn. So like this. So this is a difference between them, both of them. A is a scalar and here A is a matrix, n by n matrix, right? So before we know anything, so I'll take simple example. What I do, simple system of linear equations, x1 dot equal to minus x1 and x2 dot equal to 2x2, right? Here, actually this is a system of equations, right? 2 by 2 linear system of equations. So there is no square and all this. If you write in the matrix form, x dot equal to ax, right? Here x is equal to x1, x2, and a is simply, this is -1, 0, and this is 0 and 2, like this. So this is a, so generally, right, generally we can write like this also. But here, this in the, fortunately we are actually, this is a simple example because this x1 dash is in terms of x1 only, and x2 dash is simply in terms of the x2 dash. But in the linear system, so two ways are there, right? So here the solution of x1 of t equal to, so what about the solution here, x1 of t? Imagine x1 of t equal to some constant c1 into e raised to minus t, right? And x2 of t equal to some another constant c2 into e raised to 2t, right? Yes. Here now, so particularly we have, this is a diagonal matrix, right? So this is an uncoupled system. There is no combination in between them. Can we write this solution? See, the x1 of t, and can we write in terms of the matrix form, x of t equal to, what I do, I'll write c1 and c2 here, column type, right? So that multiplication is possible. E raised to minus t, so just imagine e raised to minus t is 0. Yes, we can write in the matrix form this combination. This is 0 into e raised to 2t. Yes, imagine. So this actually I have written this in terms of, basically this is the same thing, right? So I have written x of t is x1 and x2. So this way, right? And what is c? So this x of 0 equal to c1 and c2. So this is the initial condition. This is given. Or you may have x1 of 0 equal to c1 and x2 of 0 equal to c2. So we start from the simple example, right? So this way we calculated the solution. So this is the solution. Now imagine, right? Now we can draw the phase portraits for this example, x1 of t and x2 of t. As now relation between x1 and x2 will define, and we'll eliminate this. What we'll get? See. Now for the higher cases, the phase portraits are different, right? So minus x1, minus x2 are there. We have to draw the graph against x1 and x2 as t tends to infinity. So how to draw the phase portraits for these two? We have solution, everything. Now, so this is x2 and this is x1. So that depends upon how I. Okay, so this is x1 and this is x2. So x1 is a solution. See, so I'll go to the previous thing again. So these solutions are, these two solutions are there. So we have to draw the graph x1 against x2 as t tends to infinity, right? Here, if I square x1, right, x1 square of t equal to c1 e raised to minus 2t, and I divide by this way. So this is x2 of t equal to c2 e raised to 2t, right? If I up, so the, what will I, what is there? Now this gives you c1 square, sorry. So what we get here? Y x2 equal to, if I change here, so from this equation we can write x2 of t equal to x1 square of t by, if I put, this is another constant, k by k, right? So this is a simply, so you can see, so this is some curve. Now we have to draw the pictures of this curve as t tends to infinity, x1 tends to x2. Looking at this solution, c1 and c2, x1 equal to, or basically you choose x1 equal to e raised to minus t. Now here, see, the nature of the x1 is, as t tends to infinity, so see, I'll write, so this x1 equal to c1 into e raised to minus t, and x2 equal to c2 into e raised to 2t. As t tends to infinity, we have to calculate as t tends to infinity. So x1 t tends to infinity, x1 goes to 0, and t tends to infinity, x2 tends to infinity. Means naturally, this actually, if you see here, the direction fields are like this. If you draw or looking at these things, you just calculate at x1 and x2. See, you choose x1 here, x2 here, and you put there. So it is in terms of the constant only. So what we have x2 equal to? x2 equal to, so what we obtain? No, sorry, x1 equal to, or x2 equal to, yes, x2 equal to x1 square by k. Also like this, right? Similarly, here if you draw in the negative subquadrant, let's see. Now, in the classical case, we are having this thing, right? Classical case, we are having this thing. Again, if you do so like this. You calculate this, actually these are the points where I'm just drawing the tangent at that point. Nothing else. And if you draw the phase lines, you see. Now, along x1 equal to, see, what will happen? x1 equal to 0, see, along the x1, the solutions are, this is origin, right? Along x1, solutions are going towards the 0, right? And what about x2? Along x2, solutions are going away from this, right? So that is, if you go other things, other ways, so solutions are like this only. Now here you draw the pictures. Sorry, it will not cross the anywhere. It will either touch. So this one, arrows are upwards here. Here again. Here, this way. Here again, so this you can see. See, moving away from the origin. Okay. Here now, so in the classical, our ordinary differential equation, there the situation is one, depending upon the value. But here two situations are there. Solution on the one axis it is coming towards, and it is one axis going away from. So this is a different point, right? Now here again for the system, this x dot equal to, see, this is x dot equal to ax is there, right? So here ax equal to 0. So you find, so what is x1 equal to 0 and x2 equal to 0. So 0, 0 is the equilibrium point in 2 dimensions. So what is the equilibrium point? The definition will remain as it is, which gives the constant solution, right? X dot equal to 0. Or if you have x dot equal to f of xy equal to 0. So that the x1 equal to 0 and x2 equal to 0 gives the solution, right? So these solutions now, this is not a stable solution now. So because in the classical thing, only one, either stable or unstable. Here, so we don't know, it is in between them, right? We can't say it is a stable also, or we can't say it is unstable also. Okay. So this equilibrium point, so this is 2 by 2. Now we go for the 3 by 3 example. So we'll consider simple examples, uncoupled examples. 3 by 3 again. x1 dot equal to x1, x2 dot equal to x2, and x3 dot equal to minus of x3. Okay, here I directly write is x1 equal to e raised to t, right? x2 equal to e raised to t, c1, c2, and x3 equal to c3 e raised to minus t. So these are the solutions. Only this solution tends to 0, other tends to infinity. This also tends to infinity as t tends to infinity, right? So these are the cases. Now here, so three-dimensional, how to draw the three-dimensional? Particularly, see what happens in x1, x2 plane, the solutions are unstable, going away from. So for that purpose, I'll draw here three-dimensional picture here. So this is suppose xy plane. Okay, so this is three-dimensional xy plane. Now origin is here. Okay, this is x2. This is x1. Okay. Imagine this is origin now. It is changed now because so this is x1, this is x2. So if you concentrate on these two only, the solutions are going away from this, right? So this way. Then any other solution also, if you pass in the plane, it is going away from, right? But now what will happen with the z-axis? Sorry, third axis. If you draw this axis here. So for this axis, the solutions are the x2 and x1 is like this here. And for this in below, actually, I'm drawing this below of this. So like this. And here the solutions are coming towards. So the phase portrait for this system is shown this figure. The x1, x2 plane is referred as unstable, right? So this is unstable. And x3, it is a stable. So similarly, this is example where we have discussed simple example, right? This is x3. So I write x2 equal, sorry, x dot equal to. So this is 3 by 3 matrix 1 0 0 0 1 0 and 0 0 minus 1 into x. So this matrix I have considered here. We have considered only uncoupled system, basically only diagonal matrices are there. Okay, so this example we have discussed. Now we'll state the some results related to the matrices now. So again, I'm saying just one thing: y dash equal to ay has a solution y of x equal to e raised to a p into y0, right? So this is the solution. So can we expect the solution of x dot equal to a x is in similar way x of, but what is x of t? It is in R and this is in R here. Okay. Now see, we'll go to the directly to the fundamental theorem. So, okay, so in this, again, another thing just I want to mention here. So we are able to calculate the solution because of only this diagonal matrix. So if you see, this is a diagonal matrix, right? So this is because of this only we discussed it, right? So we'll go to the next point. Now, how it depends upon the matrix, actually this linear algebra part we'll discuss it now. So consider the system x dot equal to ax, right? What we consider the possibility A is a matrix, right? So we consider lambda 1, lambda 2, lambda n, distinct eigenvalues first. This is n by n matrix A, right? This is n by n matrix. With lambda 1, lambda 2, lambda n are the eigenvalues. There are eigenvalues. So from the linear algebra, if A is a matrix, now, so because a diagonal matrix is okay, no problem. So easily we can work out these things, right? So if you suppose the general matrix is given, but in the general also we consider the first case. A is a matrix and n by n distinct eigenvalues. So this is important. Distinct, there are types are there. So it comes into the diagonalization. So n by n matrix with the distinct eigenvalues, right? So then corresponding to these eigenvalues, there is v1, v2, vn eigenvectors are there, right? Then we consider the matrix P with these eigenvectors. This is v1, v2, vn. So which is invertible matrix, is invertible. So you recall from the linear algebra part, is invertible. Invertible matrix. Such that, how it is? This is P inverse AP is diagonalizable, is equal to lambda 1, lambda 2, lambda n. The first matrix what we consider, first case we consider A is diagonal matrix. Second, we consider the diagonalizable matrix. So P inverse equal to AP equal to a diagonal matrix, right? If you, this is the case now. So in this case, how to calculate the solution? Okay, so we consider this concept and we derive the how to find the solution. See, first case, A is diagonal matrix, right? So then the solution x of t is, so this way. See, suppose e raised to whatever the diagonal entries are. Diagonal, we consider A is a diagonal matrix with lambda 1, lambda 2, lambda n, lambda 1 t 0 0 0 0 e raised to lambda 2 t 0 0 0, right? And so on e raised to lambda n t. So this is the solution into C1, C2, Cn. We calculated it, right? So this is the solution, the first case. Now second, A is not diagonal matrix, but what we know? So that previous thing. So it has A is not a diagonal matrix, but it is a diagonalizable matrix, right? So that is P inverse AP is diagonal. Lambda 1, lambda 2, lambda n. So this matrix. So in this case, what about the solution? So we'll write it now. Suppose, right, our problem is this: x dot equal to ax, and we know that p is there. So if I put y equal to p inverse x, if I put y equal to p inverse x, that means x equal to py, because yp is invertible, right? So then, and this gives you, we can find y dot equal to p is a matrix, which is a constant matrix, into x dot, right? So, but what is x dot? So this is equal to p inverse x dot is ax. What is the ax? P inverse a py. So what we have? 1. We converted the system, which is not a diagonal matrix, into a see, this is a p. What is p inverse ap? So we have y dot equal to diagonal of this lambda 1, lambda 2, lambda n into y. So this is a simple system now we obtain, right? And we can find its a solution. In terms of y, and you resubstitute, because this is a transformation, we can x dot equal to x. So we have substituted y equal to p inverse of x. So this is a matrix. So this is a linear transformation. This gives the result, right? So first case, a diagonal matrix, we are able to calculate the solution. Second case, it is not a diagonal matrix, but it is a diagonalizable matrix. We consider lambda 1, lambda 2, lambda n are the eigenvalues, which are distinct n eigenvalues. So then we can find y dot equal to x. So this is, it reduces to the first part, right? So under this, we can find the solution there, right? What happens here? We'll get this is a canonical form, right? We get the solution of diagonal system, and under this transformation, that system gives the characterization in a different way, right? Now, so we characterize these things into, suppose, now what we consider, A is a matrix with lambda 1, lambda 2, lambda k are the negative eigenvalues, and lambda 1, lambda 2, sorry, k plus 1, 2, lambda n are the positive eigenvalues. So corresponding to these eigenvalues, right? So there is a stable space. See, we know that e raised to minus negative is there, so the stable solution is there, right? So we say that corresponding to this, so we'll have a stable subspace, which is a stable subspace. This corresponding to lambda 1, lambda k, whatever we get, which is a stable subspace or stable solution. That is, E, it is denoted by ES, and it can be written as a span of V1, V2, Vk, because this corresponds to the negative eigenvalues, and unstable equal to span of this Vk plus 1 to Vn. So we have these things. Clear? Now, so I assume you know various properties of the matrix thing. So this, every time it is not possible to find this diagonalizable thing. So this x dot equal to ax. X is a matrix, A is a matrix. What we'll discuss here, certain cases, fundamental theorem again. Now, so one of the results here we'll discuss here, basically, let lemma, the importance which gives the result, lemma, let A be a square matrix then derivative of d by dt of e raised to at. So can you imagine okay, so before this, yeah, you are not defined e raised to at. Okay, so I'll go to the proof actually. So this not e raised to at is not defined. So I'll give this thing. Exponential matrix is not defined. We'll define. Yeah, e raised to a. E raised to x is 1 plus x square by 2 factorial plus so on, right? Similarly, e raised to a is, this 1 is replaced by I plus a square by 2 plus plus so on. But in this case, here also the require here a square by 2 factorial and so on. So we'll not go into detail of the convergence and other these parts. So because this is there, so you may collect from the part, but you can define exponential of a matrix there. Okay, so this is the thing. But in which cases it is possible. So that part also is a part of the study basically. Then nilpotent and all these things. So you imagine this is e raised to 80. So we'll go for the next one. So now I will come to this lemma, right? And fundamental theorem lemma. Let A be a square matrix then d by dt of e raised to 80 equal to, so A is defined. A or 80 is one of the same thing. There's no problem. Right? We use the simple definition our. So first principle of the derivative d by dt of e raised to 80 equal to limit x tends to 0. So usual thing e raised to a of t plus h, right? Minus e raised to 80 by h, right? Our usual thing, limit h tends to 0. Here e raised to a t e raised to h, sorry, minus e raised to 80 by h. This is equal to limit h tends to 0. E raised to 80 is common, which is independent of the h. So e raised to ah minus I is the matrix by h. Okay, so this will continue. So this is equal to e raised to 80 is out of the limit, right? So as a limit, h tends to 0. So we write e raised to ah. E raised to ah is I plus a h, right? Plus a square h square by 2 factorial and plus plus so on. Minus I, this bracket close and divided by h. Clear? So this in this process, this I will get cancelled. This is equal to e raised to 80 limit h tends to 0. Here is h, here is h square. In each of this term, so here is h and I'll take one h common. So this is a plus a square h by 2 factorial and plus 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 everywhere h is there, right? So this h will get cancelled and this is equal to e raised to 80 into a plus 0 plus 0 plus 0, right? So, or you may write e raised to 80 here above. So this gives you a into e raised to 80. You see, the result is similar. E raised to 80, its a derivative is equal to a into e raised to 80. Similarly, e raised to 80, its a derivative is similarly a into e raised to 80. So this gives you. So it requires little bit other things also. So, but you collect from that, but the general result is there, right? Here, this h is sufficiently small and so on, things are required here. So that part we can consider. So e raised to h converges uniformly for mod h. If it diverges, there will be no problem. If you choose h greater than or sufficiently large, so then this diverges and it will not converge to 0. So that will not be a. So under certain condition is there. Now we'll go to the fundamental theorem of a linear system of equations. Linear system of differential equations. Okay, linear system, fundamental theorem for linear systems. Statement: let A be an n by n matrix, then for a given x0 in Rn. Now, so all these things are in n dimension. The initial value problem x dot equal to ax, and x of 0 equal to x0 has a unique solution x of t equal to e raised to at into x0. So what I said u, so this is y dash equal to ay, right? So our classical thing, it has a solution y of t equal to some constant c, or you have e raised to at into some y0, right? So see, so this is the scalar and this is the matrix for the system of equations. It's analogous things. Okay. Now we'll prove it. So if you want to prove, so the proof is very simple. So you can see, I'll give the proof and then we'll stop. If x of t equal to e raised to at x0, then x dash of t equal to d by dt of this is equal to, so x0 is outside, no problem. So we know that its a derivative is a into e raised to at of x0, right? So this is a into e raised to at x0 is x of t, right? So we have x dash of t equal to a into x of t. So that means x of t is the solution, right? So that is x of t equal to e raised to at x0 is the solution, right? So this gives the solution. Now, so there are various ways are there. So there are still certain things are now what we discuss now. So we discussed today is a dot equal to ax is a linear system, right? With x of x0 equal to some x0, right? So this linear system, A is diagonal matrix, A is diagonalizable. Then we consider the general thing is now, so we can find the solution for these cases. So first A is diagonal, A is diagonalizable. If suppose now, so another points are there. So here it's basically a diagonal matrix we consider and other things we consider. A is a matrix n by n with distinct eigenvalues. Okay, second, distinct real eigenvalues you can take. So then A is a n by n matrix with distinct complex eigenvalues. Third is n by n matrix with, again, what happens is n by n matrix with repeated eigenvalues, multiplicity with repeated eigenvalues. Fourth is n by n matrix with real repeated values and complex repeated values. Real plus complex eigenvalues. So that, and now, and fifth point, so after this also there is a, if an has a Jordan canonical form. In all these cases we are able to calculate A of t. So but it requires little more calculations and more computations is required. Now based on this, so if you classify, means basically lambda, see the actually it's the characterization what we observe from the diagonal matrix is, so if the eigenvalues are negative, okay, eigenvalues are negative, corresponding eigenvectors gives the solution which is stable. Eigenvalues are positive, gives the unstable. So this is for real eigenvalues. For complex eigenvalues, if the real part is 0, then there is a center. So we have stable subspace, unstable subspace, and center subspace. If all eigenvalues are negative, you will get the stable solution. All eigenvalues are positive, you will get the unstable solution, right? If you have mixed eigenvalues, one of the values is negative and another of the value is positive, then it is a saddle. Okay, one of the value is negative and one of the value is positive, then it is a saddle, stable, right? We can, that point is defined here. So equilibrium, and this is again at an equilibrium point. We are looking at the equilibrium point. So this actually, so just I tried my, so this is stable solution, unstable solution, and central solution. Basic idea is, so whatever we study, so it boils down to the linear algebra parts that depends upon the eigenvalues of matrix. That is x dot equal to ax. And what is important here, the diagonalization process and the exponential point to define this matrix is important. Okay. So I think, ma'am, make a continue or may I stop now? Hello?
Sir, if you want to continue, otherwise you have some 10 minutes. Or shall we take the
Okay.
discussion?
So, okay, I'll continue. Then will you take, yes, yes. I'll just,
Yes.
non-linear point I'll discuss and then I'll stop.
Yes,
I'll be
yes.
discussing.
Okay.
So the linear system is there. Now, what about the non-linear system? Suppose now x dot equal to f of x. We consider this is a non-linear system, right? System, f is f1, f2, fn, x is x1, x2, xn, all this thing. This is non-linear. Then what about this theory now related to this example? So there are two types, local and non-local. Non-linear problem. So we look at the locally. So whatever, we first find f of x equal to 0. What are the equilibrium points? And we can find the nature of the solution in the neighborhood of these equilibrium. There is a theorem by Hartmann's theorem. Again, so this f is a function from, I'll just repeat it, Rn to Rn, right? So then, so this is a multivariable case, right? Multivariable analysis. Then it's a derivative of f at x0. So this is a matrix of order n by n. Am I right? So if you have studied the advanced calculus or something like that, so then derivative of such a function is a matrix of order n by n. Okay. So then, so basically, first what we do, so we study this nonlinear problem by linearization. Okay, so we can study this problem by linearization. How we linearize? So up to this point, we discussed whatever related to this is a matrix theory, x dot equal to ax, right? So wherever we is possible to calculate the exponential of matrix, in all these cases, we find the solution of linear system of equations. Right? So, but we consider this is a non-linear equation, which is autonomous. Non-autonomous also it is equivalent, because now autonomous is in Rn, and if you consider the non-autonomous in Rn, so it becomes the autonomous in Rn plus 1. So there is no difference between them. That maximum difference is not there. So here the linearization is there. F of x. So then we have this matrix, right? So then corresponding to this, we have x dot equal to ax. Right? Again here, what is A? Now here A is particularly B of f of x0. So this is a matrix. If you have studied multivariable calculus or advanced calculus, the derivative of a function Rn to Rn gives the linear operator, and it's a matrix. It's a linear operator. First derivative. Second derivative, bilinear, right? That is D derivative, like that. It is a matrix. So this is a matrix now, right? So here now A is a n by n matrix. Now, whatever the properties, actually Hartmann proved that Hartmann and Grobman theorem is the standard theorem. So this is nature behavior of the solution of this nonlinear system and the linearized system in an equilibrium neighborhood of the equilibrium point are topologically equivalent. Means flow, whatever the characterizations are there, so they are topologically equivalent. Studying the nonlinear system, it is sufficient to study this linearized system equilibrium at these equilibrium points. Particularly, they are in which hyperbolic equilibrium point. Hyperbolic equilibrium point means the eigenvalues with non-zero real part. So that study is there, but linearization, you understand what I'm saying. So this, even though this non-linear equation is there, so we can linearize the system, and we study this, and accordingly we find the solution in the neighborhood of this particular system. That way we can do it. So means in this way we can study the linear system, non-linear system, and this actually the study of dynamical system. It is really a vast area. Just what I have tried to give the only one definition and simple examples we discussed, which are very, very simple at elementary level. So I tried to explore or introduce this chapter, and which has applications in many fields. This dynamical system, generally in the nature or in any physical phenomena or engineering phenomena, the problems are not in the linear or any simple form, so they are a little bit more complicated. Many parameters are used, and this gives the many representations are there in the for the dynamical system equations. Okay, they represent it, but this is not our task. Basically modeling they do the engineer or physicist people. So our problem is to just study these problems, find their solutions, study their behavior, study the characterize their solution, and we can link we give the proper identifications of for this particular type of example or particular type of differential equations. So that is our basic idea, basic task for the mathematics people, not the modeling. That part also one can do it, but basically so to analyze these solutions or study the differential equation in analytical point of view is important. So I tried my best to just introduce what is a linear system. I'm not able to go for this higher again. What are the source and sinks for this? But it requires a lot of time. So sometime I'll explain also. So, but today we'll stop here. From my side, I'll stop here. So open for session is open for the discussion.
Yes. Students, if you have any questions or if you want to do any discussion with Kendre sir.
Yes, sir.
So actually, it's really a new topic for our students, and you have given very nice introduction of the topic with very simple language and the definitions.
Yes, it is really. You may refer the book for Perko or maybe Hirsch and Slade, Dynamical Systems and Differential Equations, linear. So reference I just give the reference also. So
Yes.
you may refer the Perko and Hirsch and Slade. Yes.
Yes, sir. Actually, we are also unaware of this topic, and we have also understood nicely what is dynamical system.
Yeah. It's a linear algebra, 100% linear algebra, 90%
Yes, sir.
linear algebra, and 10%.
Yes, sir. Yes. It's a combination. But you have explained it very nicely, sir. There is no doubt actually in the whatever you have taught us today.
Yeah.
Yeah, from student side, if any questions. This is what situation in online teaching.
That is the problem. No one asked the questions.
Yes, sir. Okay, we will move towards the next part of this last part of this session actually for vote of thanks. I request Uzma Muchale madam to put vote of thanks for the session.
Thank you, ma'am. Am I audible?
Yes.
So, good afternoon, everyone. Today I am here for the vote of thanks of today's last guest lecture of our this series. So, we have popular mathematics lecture week we have celebrated for the National Mathematics Day 2021, which was funded by National Council of Science and Technology Communication, Government of India, and Rajiv Gandhi Science and Technology Commission, Government of Maharashtra. And first of all, I will thank to our Vice Chancellor Madam Dr. Munalini Fadnavis Ma'am for giving a permission and for motivating us to arrange such a program. Then I will thank to our today's guest lecture for explaining this topic, which is very new for our student, and also we were listening very carefully about this topic, the dynamical system. Thank you, sir, for accepting an invitation and giving a nice lecture on this topic, dynamical system. And I will thank to our director, sir, V.V. Kutte, sir, for giving us a permission and motivating us for arranging such a lecture. And I will thank to our HOD, ma'am, Dr.Jyoti Mashare, ma'am. She is always ready to arrange such a lectures for students. And last but not the least, all the students who have attended the lecture from the different colleges and universities. Thank you, everyone. Thank you, sir. Okay, over to you, ma'am.
Once again, heartily thank you, sir, for the acceptance of our invitation and taking the lecture from your busy schedule.
Thank you. Thank you.
Thank you, sir.